those of you who really want to dive into the details of machine learning a little bit more, hopefully this will be more interesting for you, this part might be a little bit more engaging for you. Another way to put it is, this morning you ate your peas and carrots, forgive me if you're a vegetarian, and now you're gonna get the steak, all right? Now we're gonna dive into hopefully understanding machine learning a little bit more. Before we get into specific algorithms, and to give you the intuition about how they work and as a model to understand the broader range of available algorithms out there, let's return to our discussion of modeling. And we left off at evaluation. All right, so a moment earlier in this section, we covered algorithm selection, then hyperparameter optimization, and then training our final model, right, given the optimized hyperparameters. So now, how do we evaluate our models properly? And some of you might already have a good sense of how to do this, but I want to cover this in a fairly extensive way because this is important to sharing your machine learning results. How do you get others to believe that your results are reliable? And how do you explain it to an audience that is savvy in terms of communicating machine learning results? So evaluation here, we want to use different evaluation metrics to understand a machine learning model's performance. I think it's tempting and very common to present one metric or maybe a couple metrics to illustrate how well your machine learning algorithm is performing. Today I'm going to argue that it's always good to at least yourself look beyond one metric, and we'll get into that in a second. So there are many metrics available. Which do you use? First off, let's consider an example of using standard accuracy, which is sort of the typical classification metric that people use for modeling classification problems. And remember, in classification, we're trying to separate out two or more classes from one another. And now let's consider that we're using standard accuracy in a data set where we have a pretty severe class imbalance. There's way more healthy people than sick people, for example. And our accuracy, our standard accuracy, is just the number of correct predictions, whether they be positives or negative predictions, over the total number of predictions we've made on the data set. So let's visualize this imbalanced data set. So here is the case control ratio. Blue is controls. In this case, this example uses fraud, but it could be disease outcome. It could be anything. And let's say this is what our data looks like in the data space. And we have our fraud cases, our small number of fraud individuals in this little corner right there. And the rest of these are not fraud. So if we're using standard accuracy, let's say we first use a model, and this is the classification boundary. And it does pretty well, right? It's getting about 90% predictive accuracy, right? It's getting all these blues on the left wrong because everything to the left of the line is being predicted orange and everything to the right is being predicted blue. Now let's say we have a model that predicts everyone as blue. Everyone's a control. This model still has a 92% accuracy, right? Intuitively, we don't want that. That is not a good model. Just saying everyone is one thing, it's not helpful. I think that's intuitive to everybody here. So, choosing an evaluation metric. It's really mostly a question of what evaluation metric you want to focus on the most. And that depends on what you're trying to achieve. It's best practice, I would say, to examine all key relevant metrics, consider them all, understand the nuances of how your machine learning model does well or poorly. And this will give you a more complete picture of performance, as well as understand the strengths and weakness of your model. Choose an evaluation metric that suits the goals of your problem. So, for example, maybe you're more interested in predicting cases correctly than you are predicting controls. Maybe you are making a predictive model of who is at high risk of COVID, right? It's much more important that you identify those high-risk patients even at the expense of calling some low-risk patients high risk, right? So there's always that trade-off in how we use a model in practice. And we also care in picking our metric is what is the outcome we're trying to predict? Are we doing classification or regression? And we're going to cover metrics for both of these here in a second. We also care, as we saw in the example I just gave, is if we're doing classification, is our data set balanced or not? When we're evaluating classification data sets. We're pretty much always going to start using a confusion matrix. The types of predictions you can get include, and you're probably all familiar with these to some degree, true positive, true negative, false positive. It's a unique combination of the actual value of the individual's outcome and the predicted value that a machine learner or a model is making. Here is an illustration of these two things. So we have, again, true positive, false positive, true negative. And we have the true class, indicated here as either positive or negative, and the predicted class. If you have a false positive, right, this is a false alarm, a type 1 error. So here's an example where positive is being pregnant. You've probably all seen this cartoon. I just can't help but use this cartoon. I love it, or this illustration. And then a false negative, something you missed. You missed a positive. It's a type 2 error, right? So in this case, saying you're not pregnant when, in fact, you are. This confusion matrix is for binary outcomes. You have two possible outcomes, two possible classes. However, you can extend a confusion matrix pretty easily. You don't need to understand this in detail right now, but just know that you can take the same idea of a confusion matrix and extend it if you have many classes. So 3, 4, 5, 6 outcomes, classes. You can still use the confusion matrix to calculate all of these metrics. Now we're going to cover specific classification metrics that are calculated directly from these four values: true positive, false negative, true negative. I really like this illustration that if any of you have looked up these metrics before on Wikipedia, you will see a figure that looks a lot like this. I've adapted it here. I've changed the colors and changed the arrangement a bit. But basically, we're taking these four elements, false positive, false positive, true negative. It's really hard to say those all together in a row. And then we have, in this illustration, we've arranged them. So we have our true class here on the left. So the true class is either positive over here on the left, that's the dark circles, the little circles, or the empty little circles, these are true, these are actually negatives. So that's the true class of the data. And then everything on the outside is what was predicted by the algorithm, and everything on the inside, everything on the outside is what was predicted negative by the algorithm, and everything in the circle is whatever was predicted positive. And so this is just a way to kind of quickly try and visualize what these different metrics are made up of as we move into the next explanation. Okay, everyone with me so far? And I do encourage you, if you're struggling with this is a great slide to go back to, or look at the Wikipedia page on sensitivity, specificity, recall, all those metrics. It's really useful to use this to break down and understand the different metrics. So the first metric we're going to talk about, I'll just quickly list them all because there's a lot of metrics and I just want you to be familiar with them. But in each metric, I've included how you calculate it with the true positive or the other positives or negatives. And then I use these shape slices to try and visually capture what's going on. So for instance, for precision, it's out of all of those that were predicted positive, that's everything in the circle, how many were actually correctly predicted positive. For sensitivity, which is also known as recall, or the true positive rate, this is the proportion of positives correctly predicted from all positives. So everything that is actually a positive. For specificity, and I'm also highlighting the section that we're using to calculate it, this is the proportion of negatives correctly predicted from all negatives. Then we have the negative predictive value. And this is out of all of those predicted negative, that's the outside, how many were correctly predicted negative. Then we have standard accuracy, which I described at the very beginning. That was the first metric, right? And so this is just how many were correctly predicted, that's true positives and true negatives, divided by all predictions. And this works perfectly well if you have a balanced data set. Totally reliable, you can use it. But I would recommend, as default, you always use this metric instead. This is balanced accuracy. It gives you the same exact value as standard accuracy if your data set is balanced. Same exact value. However, It is the average of sensitivity and specificity. And those two things focus on true positives or true negatives. So they're either focusing on positives or negatives. So basically what this does is it gives you a weighted average of your ability to correctly predict one class or the other. So it allows you to account for imbalance in your data set. So if you're going to use a single basic metric and you care just as much about predicting controls correctly as you do cases, I would recommend this metric as a starting point. Then we have the F1 score, which is the harmonic mean of precision and recall. Notably, what it excludes are true negatives. So it's really totally focusing more on making positive predictions correctly. Then we have the false positive rate, which is just 1 minus specificity. This is something you want to minimize. And so out of all the predicted negatives, what proportion were correctly predicted? And then we have two more metrics, positive likelihood ratio and negative likelihood ratio. These are typically used to assess the value of a diagnostic test. And we can use them here as a post-test to determine, if you were predicted positive or if you were predicted negative, what is the probability you actually have disease given the machine learning model's prediction. So these are all useful metrics that you can compute from these original four. I will mention, they all assume you're using a single prediction threshold. By default, any machine learner, when it has to do classification, pretty much any machine learner outputs a probability rather than a class, right? And so normally, in almost any machine learner, it assumes a probability of 0.5, right in the middle. And so if your probability is above or below, that determines if you're predicted a case or control. And all of these metrics, if you calculate them, are typically assuming that threshold cutoff of 0.5, right in the middle. But as a person who applies a model, you can decide to move that threshold. Again, if you care more about predicting positives correctly or negatives correctly. Okay, if we want to look beyond just using one threshold, another way to illustrate and evaluate model performance is with receiver operating characteristics curves. So this basically is a graph that shows the performance of classification over all classification thresholds. So instead of it just being at 0.5, you're going to move that slider of determining whether you're a case or control all the way to the left to the right. And I'm going to try and help you visualize that here for those of you that aren't familiar with ROC curves. So an ROC curve has true positive rate, which is sensitivity on the y-axis, and false positive rate, which is 1 minus specificity on the x-axis. And as I mentioned before, models are starting by assuming a threshold of 0.5. And so I'm going to show you some model performance assuming that same threshold. So let's assume, using that threshold of 0.5, this is what a perfect classifier might look like. It's always getting all the true positives and all the true negatives correct. So the model line will end up looking like this. It's in the upper left-hand corner. Here's an OK classifier, right? It has some trade-off between the true positive rate and the false positive rate. And here's an example of a classifier that really didn't do well at all. It's no better than random chance at making decisions, right? 50% for each, 0.5 for each. So the no-skill line on an ROC curve shows what model predictions would look like for a model that really just did no better than chance, no matter where you put the threshold slider. And so it would look like this. So this is the no-skill line. And now let me draw your attention to the extremes of moving the slider. First, let's look at where we have a model and we tell the model always predict positive. No matter what, predict positive. And that'll be up here. Now let's say, as a model, always predict negative. And that would be this lower part of the no-skill line, down here in the bottom left-hand corner. Now let's look at how a classifier would perform in moving its slider all the way from the left to the right, from one extreme to the other. So a perfect classifier would just be a square, taking up this whole space. An OK classifier might look something like this. Right? As we move the slider, the trade-off between true positive rate and false positive rate changes. We can use something called area under the curve to summarize performance over all these thresholds in a single metric value. So for the no-skill line, the area under the curve just comes out to be 0.5. So like accuracy or balanced accuracy, if you're not doing better than 0.5, you're not doing any better than random chance, right? We can also look at the area under the curve for the OK classifier and the perfect classifier, right? And so an area under the curve of 1 is the best you can do. Notably, if you have high class imbalance in your data set, using this curve and area under the curve can be overly optimistic. So you can actually bias your evaluation if you have a highly imbalanced data set and you use only the ROC curve to evaluate performance. And that's why I'd recommend, if you have imbalanced data, you also consider, a little bit more on ROC curve first. So to generate an ROC curve, you're going to need the class prediction probabilities from the model. I mentioned before, models don't necessarily just output a class. They give you a probability that you belong to one class or the other. And you use this to predict the outcome for each instance based on where you set the decision threshold slider, 0.5 or higher or lower. Here's a little GIF that attempts to visualize this. So threshold, that's our slider, right? And we can see that as we move our decision threshold from right to left, going this way, things that used to be a true negative suddenly become a false positive because we're moving the slider, and now something that was predicted case before is now being predicted control. And we can see that as we move this slider, our evaluation metrics are going to change because our counts of true positives, true negatives, and so on are changing also. Does that make sense to everyone? Okay. I think it's a really useful thing to understand so that you can report your machine learning results well. For multi-class outcomes, right, so this is for binary class, you can do the same thing. You can use ROC curves, but what you have to do is binarize your outcome. So if you have 3 classes, it's, did I correctly predict my class versus some other class? And so you have to make an ROC curve for each class. So if there's 3 classes, you end up making 3 ROC curves. One where I am the self class versus a something else class. Does that make sense? Okay, what I was about to talk about a second ago is if you have imbalanced data, then I recommend strongly that you make a PRC curve, a precision recall curve. This is a graph showing the trade-off between precision and recall at all classification thresholds. So instead of considering both positives and negatives equally, like the ROC curve, sort of like the F1 score, this is focused more on your ability to predict positives. So I would recommend doing this, for one, if predicting positives correctly is of more interest to you in your study, or if you have a class imbalance. This is what a PRC curve looks like. So here we have on the y-axis precision and recall on the x-axis. A perfect model in this case will appear in the upper right-hand corner, and its area under the curve would be a line like that. You're going to need class prediction probabilities like you did with ROC curve to make this. And different from the ROC curve, the no-skill line here, as opposed to just being the diagonal, here it can actually change based on the data set, because this reflects the case control ratio in your data set. If you have a balanced data set, your no-skill line is going to lay right here at 0.5, pretty straightforward. But if you have more cases than controls, right, positives divided by the total number, then your no-skill line will be higher if you have more positives. And so when you visualize this, you have to make sure that you're visualizing it correctly so your no-skill line is in the right place. And like ROC curves, we can use area under the PRC curve, PR curve, I always get that jumbled, forgive me, to summarize performance of this curve as a single metric. Any questions about this real quick? Because this is something I want to make sure everyone understands and is pretty comfortable with. I certainly go back and take time. The wiki pages on this are actually awesome. So do revisit those, and I'll make these slides available as resources, as I said earlier in the talk. Okay, shifting gears from classification to regression. Things are a little different when we're trying to predict a continuous valued outcome. We have three metrics that are commonly used. The first is mean squared error, or MSE. And this is what that equation looks like, where this right here, this difference between R, is the difference between the predicted and real values, right? Because there's a real continuous value, that is the outcome for an instance, and then there's a value that's predicted by the model. And so we take that difference, we square it, we sum them up, and we divide by the number of instances. And that's the root mean squared error. Root mean squared error is also really important as a loss function for a lot of machine learning algorithms, and we'll touch on this when we get into talking about how some algorithms work. Notably, it magnifies the impact of larger errors because of this squared, because of the power of 2, right? So anything that is a larger difference is going to have a larger impact on the model performance. The downside is that you get units that are squared when you report this metric, and that can be confusing sometimes. So as an alternative, you could also have root mean squared error as a metric. So here, you preserve your units, right, because you're squaring everything. And then the last metric we'll mention here today that's commonly used is mean absolute error, or MAE. Again, here units are preserved, but because there's no squaring and we're using an absolute value difference between our two values, we don't weigh larger differences more than smaller ones. Of quick note, just to draw your attention, if you didn't notice, when you're doing classification, you're usually looking at accuracy, which is something you want to maximize. You want the biggest accuracy possible, and in regression, typically when we talk about it, we're talking about error, and we want to minimize error. For classification?
For this one, what would you want to use, the mean squared error or root mean squared error? Instead, it seems to make sense that mean absolute error would not assign greater values to bigger errors, right? Like what would be the purpose of using one over the other?
The difference is subtle. So he was asking why, in what situation would you use one or the other? And the short answer is I don't have a fantastic explanation for that handy, other than to say that sometimes you pick one metric because when you go to do the calculus behind optimization in some of these algorithms, it's much more convenient and algorithmically efficient to use a certain form of this expression, a certain form of error, because it's easier to calculate quickly. That's one reason. Another is when you're modeling, you might specifically want to make errors as small as possible, right? It's okay to have little errors for the purposes of your model. That's okay, but big errors are a big no-no, in which case this would be something you'd really want to use. Is that fairly? Okay. Okay. All right, so we talked about model evaluation, and we're going to end modeling talking briefly about feature importance estimation. So here, we're talking about measuring or estimating the contribution of individual features from your data set to the performance of your supervised learning model, right? This is a little different than feature selection and feature importance, where you're early on before modeling, you're evaluating feature importance as a way to filter out features that you don't want to keep. Now we're asking, once we've made this model, what features are driving the predictions, the accurate predictions? So, okay, we do this to better understand the data in our model, but also we can do this to facilitate another round of feature selection and remodeling. As I mentioned earlier, machine learning modeling can be a cyclic process. You could run it once, see what features seem to be important. You could run it again, having selected as an expert and looked at the results, this set of features seems to do better. Maybe I can make a simpler model that works just as well. Notably, some, but not all machine learning algorithms offer a built-in strategy to estimate feature importance. So random forest, for example, is one of those algorithms that has its own internal feature importance estimation. And it does this with out-of-bag estimation based on how it does sampling to build the trees. And we'll get into this in a second. But the point is, not all machine learning algorithms have a way to access feature importance by default. All they give you is a model. They don't give you a way to look at feature importance. So these, and also even the algorithms that do have this, that do have a way to look at feature importance, they don't always evaluate feature importance the same way. So if you go from a random forest to a rule-based machine learning algorithm or logistic regression, the way you would glean feature importance doesn't really mean exactly the same thing. So if you go to compare feature importance from one algorithm to the next, and they're each using their own way to estimate importance, sometimes it's hard or impossible to directly compare them. So an alternative is to use a uniform approach, something that you apply the same way to all methods. Now this has its own strengths and weaknesses, but one such method is a permutation-based approach. And basically what this does is that it takes your trained model, takes your evaluation testing data set, and evaluates it, right, the first time. You get an original model testing accuracy. Then, for each feature, one at a time, you shuffle the values for just that one feature, effectively attempting to randomly obliterate the relationship between that variable and the outcome you're trying to predict. And then you take that data set and see how well the model works now. Did the model work worse? If so, that feature presumably had an impact, right? It had an importance to making good predictions. And it actually does this many, many times, right? It permutes, it shuffles a bunch of times and reevaluates, and then uses this to estimate feature importance. And you can do this for any machine learning algorithm. And I should mention that's not the only way to do it. It's just the one I've been using recently and I find works pretty well, but it has its own advantages and disadvantages. Okay, so now we've covered all of modeling. But before we move on to post-processing, this is where we're gonna get into a little bit of the nuts and bolts of how machine learning works. Just out of curiosity, because I can decide to go through this faster or slower, depending on interest, how many of you are actually, like you hope to take away some understanding of how a few machine learning algorithms actually work? So raise your hand if you do want to understand that. Okay, so I'll sort of try and do a nice balance, but hopefully you all get something useful out of this. We're gonna start really simple and then dive into something hopelessly complex that I will not cover at a deep mathematical level, but instead trying to impart an intuition about the basics of how they work, so you have the basic sense. Okay, so a closer look. We're gonna start by looking at decision trees. Pretty easy to understand as far as machine learning algorithms go. I want to use that as a jumping off platform to understand a number of really other popular methods, because they're all based on decision trees. Specifically, we're going to talk about bagging decision force, which is just decision tree with bagging. I'll explain that in a second. Random forest, which many of you might have heard of. Adaptive boosting, and then gradient boosting. These methods down at the bottom are some of the most popular and successful machine learning algorithms out there next to deep learning. They have won, variations of these algorithms have won a ton of machine learning data science competitions. Okay. And then lastly, because it's everywhere, I'm going to talk a little bit about neural networks and deep learning. Okay, let's start with decision trees. First off, when you hear decision tree, depending on the context, it can actually mean two things. First off, it could just be a decision support tool, just a way to present information, right? Does it move? Yes or no? What tool should you use, right? I didn't learn from a data set to put this together. I took my expert knowledge and used it to show how to make decisions in different contexts. Decision tree can also be a machine learning algorithm where you hand it data set, supervised data, and it learns how to make splits so that you go from the top of the tree down to some leaf of the tree where a prediction is made, a determination of your class, or a determination of your quantitative outcome. First, let's cover some terminology to better understand what we're talking about for a decision tree. Up here at the top, this decision node is also known as the root node. All data points enter here. So no matter what instance you are, you start here when we're applying the tree to make predictions, and then you shuffle down the tree like, what's that game, Plinko? Is that what I'm thinking of, Plinko? And so all instances enter here, and then get divided during the training of the algorithm, ideally into more homogeneous groups. More homogeneous meaning that as many people in the leaf belong to the same class or have a similar outcome value if we're doing regression. Decision nodes are really anywhere where you make a split below it into one group or another. We also call these subnodes, internal nodes, split nodes, or chance nodes. Down at the bottom, we have leaf nodes. These are nodes that don't split, and this is where the predictions are made. We also can call these terminal or outcome nodes. There's also these terms parent and offspring nodes. A parent is really anything above, and a child obviously is below. Splitting is what occurs at a node, so you split your instances on one direction or another. And then we have this idea of a branch or a subtree. It's just a subsection of the decision tree. And then lastly, levels or depth, right? A tree can be grown to a certain length, a certain depth. The simplest is just a tree with one split. You can have a decision tree that's basically a linear classifier that just splits on one thing. Or you can grow it to an extremely large depth. But like a lot of machine learners, the deeper the tree, the more likely are you to overfit, right? Interpretation. I want to mention this plus for decision trees. I mentioned earlier on, there's very few algorithms out there, machine learning algorithms, that are truly interpretable. That you really can understand how the decisions are made. And this is one of them. So one nice thing about a decision tree, in terms of interpreting it, is you can linearize a tree, any tree, into a series of simple decision rules. And you do this by following any path from the root node to some leaf node. So where the rule outcome, so whatever's predicted by the rule, is the value at the leaf. So here's an example. A rule might be if condition 1 and condition 2, then outcome. So taking an example from this tree, let's follow a path. Is it rain? So if it's not raining, no, don't bring anything. So here's a rule that we can easily interpret as a human being. If this happens, do this, and so on and so forth. Make sense? Splitting. So the most basic decision tree implementations only split each node into 2 other nodes, but you can actually have more complex implementations than that. So some allow splitting more than 2. I'm going to show you how splitting occurs if we're splitting on a feature that is either categorical or numerical. So categorical, let's say sex assigned at birth, male or female. So we have, you can go one way or the other, and it's just yes or no, true or false. Differently, if you have a numerical value, you're using a threshold. So if age is greater than or less than a value, you go one way or the other. Pretty straightforward, right? Then we have leaf node prediction. How do we make a prediction at the end if we're dealing with classification versus regression? So first, let's look at classification. Categorical outcome. So let's say it's sick or healthy. So we look at the instances during training that ended up in this leaf. Who from our data set ended up in this leaf? And if there's a larger number of class blue than class red, anyone who's predicted in the future that ends up in this node will be assigned class blue as a prediction. And the probability of that prediction, roughly, it's not a perfect estimator of probability, but is the proportion of blue to red. And we can also do this with multi-class, depending on the implementation. Differently, for regression, and the intuition here is that decision trees are not as good at regression, because it kind of does this in a cheating way. Let's say we're trying to predict a continuous value outcome like height. The prediction we make is we look at the instances in the leaf node, and we look at the distribution of values, and we look at the average. And the average outcome for the people that end up in that leaf, they get that average as the prediction. Does that make sense? So it's not terribly sophisticated how predictions are made there. Okay. This is a really fun visualization showing a pre-trained tree, and we're taking first a training set and then a testing set, and we're running it through the algorithm. You can see here the training data gets 100% accuracy because it's overfitting. And then our testing data set gives us still pretty good accuracy, but not that great. And you can see how individuals of either class follow a path down the tree, end up in a leaf, and are either correctly predicted or incorrectly predicted. Make sense? Okay. Training the model. So actually, how do you grow this tree? We start at the root node, right? We don't have a feature picked yet, but we're starting at the root node. And what a decision tree does is recursively identify a feature that best divides your whole data set, or whoever is in that node currently, into two subnodes that are maximally homogeneous, as I mentioned before. So, as purely one class or as purely the other class. And this is called Hunt's algorithm. And so the best feature is determined heuristically. It tests different features and figures out which one to split on, and if there's a threshold involved, what threshold to split on. And then we evaluate these splits based on heuristics that determine homogeneity. And here's some examples. There's Gini index, information gain, chi-square, variance reduction, and different decision tree implementations might use different metrics or have different metrics as different hyperparameter options for you to use. And then the tree stops growing, like it does this one level after another, once maybe you've hit a maximum depth that the user specified as a hyperparameter, or some other constraint that tells the algorithm to stop growing. So here's an example. Let's take a look at trying to train a couple splits of a decision tree. We're going to use this example of predicting credit risk, just because it's really simple. We want to classify whether you have good or bad credit, and we have two features. Have you spent less than 2 years at the current job, yes or no? And have you missed any payments in your life, yes or no? So what feature here do we want to split on? So our first option is a split at our root node based on new job. And here's our original count of good and bad classes in our data set. And here is the resulting purity in either branch. Contrast that with using missed payments as our first split, where we have this level of homogeneity in both. Show of hands, do you think the right side, raise your hand if you think the right side gives you the better homogeneous split. Raise your hand. How about the left side? Raise your hand. So it is the right side. It's a little hard, it is subtle. Don't worry if you didn't get that right. It's subtle, but more of the giveaway is you can see that there's a real large number of good on this side and only gets one wrong, and that sort of drags the homogeneity of that split and makes it better than this one. Now, after we've picked that first split, we can look at the second and see if we can further improve our distinction of one class from the other. And in fact, we can when we add this second feature. Now we get an even higher level of purity in one of the branches. Now let's look at subsequent splits down the tree. We're not going to do this in detail, but I want to visualize what a decision tree is doing in terms of a problem space. This is very similar to the yin-yang data set I showed you earlier. We're trying to separate out two classes. We have x and y axes, which are represented by the variables x and y over here in the decision tree. So our first split is y is greater than 0.5. That's this first line. We can see the resulting instances that end up in either leaf, either the red square or the black one. Okay? Now we've done an okay job classifying so far, but obviously we need to split more to do a better job making good classifications. So we have another level of splits, this time using the x variable. And we can see now our red leaf does a perfect job classifying all class blue. There's no wrong answers there. So we're done growing that branch of the tree. We don't need to grow it anymore. Our black leaf, right, still has a pretty big mix. That could use some more separation. So we're probably going to grow that further. Then over here, the yellow square, we have all greens, so we're good. We don't need to split that anymore. And then lastly, orange, we have all but one. And depending on how we set our hyperparameters configuration, it could still try and grow this further, this branch, or it might stop here, decide it's pure enough, we're good. If we keep splitting, hopefully you can see how decision trees try and parse out this boundary space, right? And it can get a more and more sophisticated nonlinear boundary, even at a much greater depth in the tree. So you can see we can get a pretty refined decision boundary. Okay, to summarize decision trees, yeah?
When is
It's a great question. It's hard to tell from this, right, because it's just training. You really only know when you compare your training accuracies to your testing accuracies. At that point, you can see the degree of overfitting. So if your training and testing accuracies are very close, it's pretty minimal overfitting, and the opposite, if the opposite's true. Advantages and disadvantages. So advantages, they're an easy to understand algorithm. They mirror human decision making. They're an interpretable white box model. They're useful in data exploration. They have data type flexibility that can handle continuous categorical variables, outcomes that are discrete or continuous. They're non-parametric. They don't assume a model configuration, so they're pretty flexible. And they also conduct internal feature selection, as well as performing pretty well with large data sets in terms of efficiency. They're pretty fast algorithms. Disadvantages. They are prone to overfitting, like all machine learners, but some are better than others at this. They're not very robust. A small change in the training data set could have given you a wildly different model, right? So that is something to keep in mind. They're not ideal for numerical outcomes, for regression, as I showed you, right? It's trying to predict a value just based on the average of the instances that ended up there. So it might not be quite as accurate as some other methods. It's also myopic, and what I mean by that is technically they can capture interactions, but we've shown empirically that as the number of features in your data set increases, it becomes impossible for them to reliably detect interactions because it has to do a split looking at one variable at a time. And we covered earlier, when you're looking for interactions, you need to consider them together. So you can technically detect interactions, but it's really only pure luck that you're able to capture them with a decision tree. And they have a bias towards features with more categories in categorical variables if you're using Gini index as a homogeneity metrics. All right, moving on from the basic decision tree, let's talk about ensembles as a gateway to a bunch of other tree-based methods. So ensembles are a group of models trained on the same task, and they're taking advantage of wisdom of the crowd, as I mentioned earlier. There are a few general ensemble types. First is for classification. This is a hard voting strategy where you train different models, and all of these models vote where the majority class is the final prediction. Something like this. So you have an original data, you have trained, let's say 4 models. You have a new input instance and you're trying to make a prediction as to whether they're a case or control. And all models make a prediction and then they vote and we pick the majority. Make sense? For regression, similar, we train multiple models, but now we average their predictions, and the average becomes what is predicted. Then there's this more advanced idea of stacking. So here, you have a meta learner that sits on top of a bunch of other algorithms that have been trained, and it learns from their outputs. So you train, let's say, 4 models using whatever algorithms you want, and then you take their prediction outputs and feed it into another algorithm that's learning from all the other one's outputs. And this meta learner then trains itself to make a final prediction based on the outputs of all these other models. Lastly, there's the ideas of bagging and boosting that we'll talk about more specifically when we talk about some other ensemble methods. Okay, a quick note, ensembles are great for giving you more reliable performance in making predictions. Less variation from one data set to data set, one person to person. However, the inherent trade-off is they become more difficult to understand how the predictions are being made. Okay, so we're gonna explore some different decision tree-based methods. We started with decision trees, and then we're gonna talk about bagging, and then how that leads to random forest, then the topic of boosting, which brings us to adaptive boosting algorithms, then gradient boosting, which brings us to some of the most sophisticated tree-based methods that people are using very, very frequently nowadays. These are all tree-based ensemble methods. And so let's start with bagging. So bagging, also known as bootstrap aggregation or bagging decision forest. This is an ensemble meta algorithm that trains independent classifiers on subsamples of the original training data set. It does this to reduce overfitting and variance, And it's really useful for models that have high variance, high capacity modes like decision trees. So this is the procedure. It's really, really simple. We have an original training data set, and we sample with replacement from this data set. And so we're basically sampling this as if this were the population. And then we train models on each subsample. Then we take all these models and combine them to make a vote. Pretty straightforward. And what's also nice is any samples from the original training set that didn't make it into any one of these can also be usefully held out as an out-of-bag estimator of model predictive performance. Okay, that's bagging. That is one ensemble approach you can use with decision trees. Now let's take that a step further and explain a random forest, which is pretty similar. A random forest is just like a bagging decision forest, right? We're using samples of instances, but this time, every time a decision tree makes a split, it only has access to a random subset of the features in the data set. So while it's growing trees, trees are grown on a subset of data instances, and splits are decided upon based on random subsets of features. This gives you a much greater variation in the trees that comprise your population of trees, the ensemble of trees used to make predictions. And so just like the last one, it's, our final decision is bringing together the predictions in a voting scheme of all of our individual trees. Random forests are a super reliable machine learning algorithm. I would say if you're looking for an easy starting point in machine learning, like something you just want to run quickly and get a sense of how well your algorithm works or how well your data set, how much information there seems to be, this is a great starting point. They're pretty reliable. They don't take too long to run. There's a lot of advantages to random forests. But they're not perfect. No method is perfect. No one ring to rule them all. Okay. Next up, boosting. This is actually pretty easy also. It gets a little more complicated when we get to gradient boosting, but boosting. So here, this is an ensemble meta algorithm that's going to combine weak learners into a strong one. Think of, not Transformers, what's the old cartoon where the robots combine to make a meta? What is it, Ultron? Voltron, thank you. Kind of like that. So we're going to iteratively learn weak learners. And by a weak learner, I mean something as simple as a one-level decision tree could be a weak learner. And we say, okay, here's our data set, our classification data set. We're trying to separate out red from green circles. Forgive me for people that are red-green colorblind. So here we basically have a linear decision boundary. It's a one-level decision tree. And then we look and say, well, what instances did we incorrectly predict? And then, in a subsequent round of weak learner training, we upweight the importance of predicting that one we got wrong. So now, in the next weak learner we train, we've now almost insisted that it classify that individual correctly. And we do this again and again and again and again. And we put them all together, basically stitch them together like Voltron, right? And we form our strong learner. However, this method, as I've described it, super easily defeated by noisy data and outliers, very sensitive to those things. And the well-known implementation of this basic strategy is called AdaBoost. Okay, now on to the, I don't want to say nasty stuff, because I think it's really cool, but this is harder to understand. I will do my best. I'm going to point you to some useful videos. If you're unsatisfied with my level of explanation, I found incredible videos that I think do a great job explaining every little mathematical detail to someone who hasn't taken calculus since high school, okay? All right, so gradient boosting. In contrast with regular old boosting like AdaBoost, gradient boosting is iteratively, one after another, training weak learners, in this case, let's say decision trees, on the remaining errors or the pseudo-residuals of the strengthening meta-learner. So as you're putting parts on Voltron, you are constantly looking at the error, and you're training the next part you put on Voltron based on the errors made by the partially assembled Voltron so far. Forgive me for overusing the Voltron example, but I like it. It's great. This is an illustration of that. We start with just a decision tree. It has some errors. And then we train a new model. We're adding another decision tree to it that has been trained on these errors. We're basically trying to predict the errors themselves. And we're stitching that on to our original model. We do this again and again and again. This is basically just another way of giving importance to those instances that were difficult to predict, just like in AdaBoost, just like in regular boosting. Just a more sophisticated way of doing that. And each successive model, as I said, works in the areas of the one that came before it. As you might imagine, this overfits super easily, as it is right here. Typically, this process, to do this, you have three parts. You have a weak learner to make the predictions, like a decision tree. You have a loss function that you're trying to optimize. For instance, mean squared error could be your loss function. If you're doing regression, or log likelihood if you're doing classification. And then lastly, an additive model where you're piecing on each subsequent decision tree. So those three parts make this system. Are we on time? Okay. Okay, so let me go into a little bit more detail here. I think this is cool. So to minimize the error with each piece added to Voltron, we're gonna need to optimize this parameter gamma. It's a pseudo-regularization parameter similar to the coefficients you put into a regression model, right? Where you're trying to say this is the weight importance of this variable, the importance of this variable. You're kind of doing the same thing, but with each new decision tree you stitch on. So here this might be the first iteration. You have your final model, f, based on your x, those are your variables. You have an original gamma weighting of your first decision tree, and there's some error associated with that first model. So just like in linear logistic regression, when you're trying to optimize the coefficients that control how the line fits, right? Depending on how you adjust those coefficients, the line fit is better or worse, and your error is bigger or smaller. This is that error function. So this is the visualization of how much error there is based on one of the coefficients that you're trying to optimize, either in logistic regression or here in this function. And so ideally, we want to minimize error. So we're trying to find this minima. What value of gamma gives us the lowest possible error? Make sense so far? This is what makes gradient boosting, is that when we start with some random gamma, it could have a pretty high error, and we need to go down this gradient to the minimum. That's where gradient comes from. And to do this, we're trying to minimize this loss function every time a new weak learner is added. So we start with this first equation, we find this minima for gamma, and then we minimize that error. Then we add another decision tree that was trained on the prior errors from the last function, and we decide its new gamma. This new parameter, this v-looking thing, new, that is a learning rate. That is a hyperparameter specified by the user. The smaller you set that, the slower the algorithm converges on an optimum, but the more easily it does so successfully. If you make big changes each time to your algorithm, it's gonna go all over the place. You want it to converge on an optimal model as quickly as possible. And basically, this just happens again and again. We add decision trees that have been trained on the errors, we minimize the error, and we move on to the next step. We just do this until we can't minimize error anymore. How do we find gamma? So how do we pick the gamma that minimizes the loss function? We use calculus for this, right? We're gonna take the differential of this function to find the slope of this cost function, right? So let's say this is our first guess of gamma up here. Actually, in this example, I'm gonna use linear regression again as an example. We're trying to fit a linear regression line, and we fixed the y-intercept, and we're just changing the slope of this line. So there's only one parameter in this function we're trying to optimize, and this is showing how that minimal error changes as we fit this line. So early on, we're up here, we're at a high error, and then we're converging on the minimum. We're doing the same thing with gradient boosting. So we can take the derivative of our error function. And either we can set it to 0, which we know is the minimum, and just solve for gamma. But we can only really do this when there are a small number of parameters to optimize at once, when the math is simple. When the math gets more complicated, you have lots of parameters to optimize at once, then you have to turn to gradient descent. How many people here have heard of gradient descent? Just a handful of people, okay. This is used in a ton of machine learning algorithms. This is a really important thing to try and understand if you really want to understand the bulk of popular machine learning algorithms. And we're gonna take a break here in just a second. Let me see what time. Okay. So this is used everywhere. And you can use it to optimize one or more parameters of a function at the same time. So for instance here, going back to linear regression, we're optimizing the y-intercept and the slope at the same time. So there's two parameters. Here on the right, we can see the error function for just one of those parameters. If we were looking at visualizing both at the same time, we'd have to have a 3D visualization to see how we're finding a 3D optimization. And if you have more than two parameters to optimize at once, now you're talking about hyperspace, right? You're talking about n dimensions of space that you have to find a minimum in. And it gets mathematically very complicated. So notably, gradient descent is what we call first order optimization. We're only using the first derivative when optimizing parameters. And gradient descent has its own hyperparameter, its own learning rate. And basically, this determines how big a step it makes each time. So it's going to iteratively take steps towards the optimum, and each step, each time, the size of the step it takes is based on the learning rate you specified times the derivative, the slope. So the farther away you are from the optimum, the bigger a step is taken. And as you get close, it takes smaller and smaller and smaller steps until it hopefully converges on the perfect optimum. Notably, to use gradient descent, your features should be scaled ahead of time, like we talked about way back in data preprocessing. If you want to learn more about this, if you want to understand the mathematical steps, check out this YouTube link. This is an awesome set of YouTube videos on machine learning by a guy who he calls his channel StatQuest. He says BAM a lot. Anyone, have you heard of StatQuest? Yeah, awesome. So this is a great video on gradient descent. I like this visualization explaining gradient descent. This golf analogy I think is great, right? Because when you're far away, you're going to hit a longer shot. And then as you get closer to the hole, you're going to take smaller and smaller hits. Sometimes you might go over, but then because the slope is in the opposite direction, you know to take a step in the other direction, always converging towards the optimum. There are a few variants of gradient descent I want to mention because they're useful to know. The first is batch gradient descent. This is where all training instances in your data set are used to calculate steps towards the optimum. Mini batch, which you might hear when people talk about deep learning, all it is a random sampling of instances to speed up this approach. That's all it does. And here we can see this is batch gradient descent, and you can see that there's a more random search when we use mini batch because it doesn't have all the instances each time. And then the most extreme is stochastic gradient descent. It's only using one instance each time to take a step towards the optimum. So its path is super chaotic, but it has some really important advantages, like it allows for the best generalization. It helps overfitting the best. Last thing, and then we'll go to break. I just described gradient boosting, talking about gradient boosting in general, like how you would do it for any weak classifier. And I kept mentioning decision trees. Technically, if you're using decision trees as the weak classifier, these gammas are actually learned for each leaf of the tree. You don't need to know the details here, but if you want to, first off, this is a visualization of gradient boosting tree working, just to give you an idea of how it's trying to fit its model. And if you really want to learn all the details of gradient boosting trees, again, these are StatQuest links, awesome videos, love them, can't rave about them enough. Oh, last thing, I promise. If you're interested in gradient boosting, there are a few flavors of gradient boosting out there that are super popular. XGBoost has been around the longest. It adds regularization to the optimization process to avoid overfitting, specifically L1 and L2 regularization. It also implements parallel computing, so it works 10 times faster than your standard gradient boosting approach. 2006 saw the release of LGBoost, or light gradient boosting. It uses some other special algorithms I won't get into, but it's much faster than gradient boosting, and it's generally a better approach when dealing with larger data sets because it's faster and more efficient. Lastly, there's CatBoost, the newest of the set. This one is my understanding it's been winning machine learning competitions left and right. It's a super popular algorithm. And it most often seems to outperform the other two, but it's not always as fast as light gradient boosting. So we've covered decision trees, bagging decision forests, and random forests that improve modeling performance from decision trees as well as generalizability. We've covered boosting, which improves modeling performance, but with an increased risk of overfitting and a loss of interpretability. And lastly, gradient boosting with these different flavors, which gives the highest tree-based modeling performance, but again is least interpretable and still has some risk of overfitting.